Section: Introduction. In this section, we will discuss how large language models, LLMs, have transformed natural language processing, NLP, by going through pre-training, supervised fine-tuning, and alignment tuning. Alignment tuning is crucial for ensuring the model's safety and usefulness. Reinforcement learning techniques like proximal policy optimization, PPO, are important during this alignment phase, even though they can be complex. To simplify reinforcement learning in LLM training, direct preference optimization, DPO, has become popular for its effectiveness. DPO involves creating preference datasets using human or strong AI judgment to choose preferred responses to questions. These datasets are used to train LLMs by comparing the probabilities of chosen and rejected answers. However, it can be challenging to obtain these probabilities with models like GPT-4, which do not provide log probabilities for inputs. In such cases, a weaker model like the base SFT model is often used as the reference model in DPO. We suggest that using a more aligned reference model would be better for DPO training and alignment tuning. One option is to use open-source models that have already undergone alignment tuning. However, this may not always be feasible due to various reasons. Instead, we introduce stepwise DPO, sDPO, where we use preference datasets in a step-by-step manner during DPO training. In each step, the aligned model from the previous step serves as the reference model, leading to a more aligned reference model for the current step. Empirically, we demonstrate that using sDPO results in a better final aligned model. While other methods focus on generating new preference data iteratively, our approach utilizes existing preference datasets. sDPO can be easily applied to any preference data and can be combined with other methods in the future. To understand the importance of using a well-aligned reference model in DPO, we conducted preliminary experiments using the ultrafeedback dataset on Mistral 7b OpenOrca and OpenHERMES 2.5 Mistral 7b as the SFT base model. We compared different reference models and found that using an already aligned reference model like Intel 7b DPO resulted in the best performance. This highlights the significance of the reference model's alignment in achieving a high-performing aligned model. We propose sDPO as a solution to leverage more aligned reference models in the training process. In sDPO, we suggest using preference datasets step by step instead of all at once. The reference model is used to calculate the log probabilities of the preference dataset, with each step using only a subset of the data. The reference model is initialized as the aligned model from the previous step, ensuring a more aligned reference model than traditional DPO. For subsequent steps, the target model is also initialized as the aligned model from the previous step, rather than the base SFT model. This approach ensures that the final model trained with sDPO has been trained with the same amount of data as a model trained with DPO. Section Summary. In this section, we introduce the concept of using stepwise direct preference optimization, sDPO, to enhance the alignment of large language models, LLMs, during training. By utilizing preference datasets in a step-by-step manner and using more aligned reference models in each step, sDPO aims to improve the performance of the final aligned model. Our experiments demonstrate that employing a well-aligned reference model, such as Intel 7b DPO, can lead to better model performance compared to using larger but less aligned models, highlighting the significance of the reference model's alignment in the training process. Section: Intuitive Explanation. In this section, we delve deeper into sDPO by reorganizing the DPO loss. We define various terms such as the preference dataset D, the question X, the chosen answer Y_W, the rejected answer Y_L, the model's learnable parameters, theta, and the policy function, pi. The goal is to minimize the DPO loss, L_text, DPO, pi_theta, pi_ref, to ensure that the log ratio gamma_pi_theta of chosen and rejected answers is greater than gamma_pi_ref, set by the reference model. As we progress through steps in sDPO, the reference model becomes more aligned, causing gamma_pi_ref to act as a stricter lower bound, leading to a curriculum learning approach from easy to hard tasks. For training, we use a fine-tuned Solar 10.7b as our base model S due to its exceptional performance and rare size. Since there is a lack of open-source models of similar size, using sDPO becomes essential. We employ OpenOrca and UltraFeedback cleaned as preference datasets and follow similar training hyperparameters. Our sDPO process involves two steps using different datasets D_1 and D_2. In terms of evaluation, we focus on 4 tasks from the Hugging Face OpenLLM leaderboard and report the average scores as H4. We exclude certain tasks to manage experiment complexity. The results of applying sDPO to the SFT base model are compared with other models, showcasing improvements in performance. Ablation studies involve comparing models using all DPO data at once versus stratified sampling. We observe that sDPO yields better results overall, especially in tasks like ARC and truthful QA. This suggests that sDPO could be a superior alternative to traditional DPO training. Additionally, the specific way of splitting the DPO data impacts performance, with using different preference datasets proving to be the most effective in our experiments. Exploring different ways to define these datasets could be a promising avenue for future research. Section Summary. In this section, we rearrange the DPO loss to gain a deeper understanding of sDPO, where D represents the preference dataset, X is the question, Y_W and Y_L are the chosen and rejected answers, theta denotes the model's learnable parameters, and gamma_pi, X, Y_W, Y_L, is the log ratio of chosen and rejected samples with respect to the policy pi. By training the target model to have gamma_pi_theta greater than gamma_pi_ref, where gamma_pi_ref acts as a lower bound set by the reference model, sDPO induces a curriculum learning from easy to hard optimization tasks as gamma_pi_ref becomes stricter over training steps. Section: Effectiveness of sDPO in terms of alignment tuning. In this section, we explain that in our method, the reference models are more aligned, leading to a stricter lower bound denoted as gamma_pi_ref. We confirmed this through experiments by comparing the mean gamma_pi_ref values on a specific dataset for the reference models in the first and second steps of our method. The first step reference model, denoted as S, had a mean gamma_pi_ref of -38.60, while the aligned model from step 1, denoted as M_1, had a mean gamma_pi_ref of -25.10, showing an increase of 13.50 in log scale. This increase indicates that a single step of our method significantly improves alignment, leading to a more effective aligned model. We also examined the mean gamma_pi_ref of M_2, the aligned model from step 2 of our method. Unlike S and M_1, M_2 was trained on the dataset used for evaluation. The mean gamma_pi_ref of M_2 was 84.35, much higher than that of S or M_1, suggesting potential overfitting of M_2 to the evaluation dataset. This highlights the risk of using open-source models as reference models instead of our method. Furthermore, in our method, the target model in each step is initialized with the aligned model from the previous step to ensure consistent training with the same data amount as in the traditional method. Although this design choice may make training the target model more challenging as steps progress, initializing the target model with the previous aligned model was preferred for stable training. Initializing the target model with the base model S resulted in a higher initial loss compared to using the previous aligned model, potentially leading to unstable training due to differences between the reference and target models. Therefore, for stable training, we opted to initialize the target model with the previous aligned model in our method.